Hey everyone, and welcome to The Explainer. Today, we're diving headfirst into a really fascinating medical mystery. We're going to look at what exactly happens when the body's red blood cell factory starts putting out defective materials. Specifically, we're zeroing in on a group of blood disorders known as hypochromic anemias. I absolutely love unpacking these clinical puzzles because, honestly, once you understand the underlying mechanics of it all, everything just kind of clicks into place. So let's just jump right in.
500 million people. Just let that number sink in for a second. That is a massive global health issue, and yet it's mostly hidden right in plain sight. These are folks walking around every day with profound fatigue, weakness, constantly feeling short of breath. They're basically all sharing this exact same invisible exhaustion. But why? Well, it boils down to the fact that their bodies are struggling with a fundamental biological supply chain issue. And to figure out exactly what's going wrong, we're going to have to play the role of a diagnostic detective. To kick off our investigation, we really need to get our definitions straight. When we look at these blood cells under a microscope, we categorize them based on how they physically look. Hypochromic literally translates to pale, and microcytic means small. So we're dealing with pale, small red blood cells. Now, the cool part, well, clinically speaking anyway, is the why. This whole thing happens because of a defect in hemoglobin synthesis. Think of it like a literal factory. When the factory doesn't have the right raw materials, or maybe the blueprints are completely wrong, it pumps out these substandard, undersized products. In the clinic, we define this as having a mean corpuscular volume, or MCV, under 80, and a mean corpuscular hemoglobin, or MCH, under 27. Okay, here's our clinical flight plan for this explainer. First, the pale, small cell. Second, the primary suspects. Third, iron deficiency versus chronic disease. Fourth, thalassemia and sideroblastic anemia. Fifth, the diagnostic detective work. And finally, number 6, management plans.
Section 1. The pale small cell. Visualizing the disease.
While the general signs of this oxygen deprivation are things like headaches, a racing heart, and that crushing fatigue we mentioned, we also have some incredibly specific physical clues that really ground this medical theory in human reality. For instance, you might see a remarkably pale conjunctiva. That's when the mucous membranes inside the eyelid completely lose their healthy pink color because the hemoglobin has dropped so significantly. Another big tell is something called colonychia, which are these distinct spoon-shaped nails. It's a highly specific physical sign intimately tied to prolonged iron deficiency. Spotting these signs, that's the very first clue for our clinical detective.
Section 2. The primary suspects. Rounding up the culprits.
So let's look at our lineup. The most common culprit by far, the one responsible for the vast majority of those 500 million cases worldwide, is iron deficiency anemia. But a good detective doesn't just jump at the most obvious conclusion, right? We absolutely have to rule out the other suspects. We've got the anemia of chronic disease, which we'll just call ACD. We've got genetic defects like alpha or beta thalassemia. Then there's sideroblastic anemia, a pretty rare condition called IRIDA, which stands for iron refractory iron deficiency anemia. And finally, environmental factors like lead poisoning. Our main job here is to figure out exactly which one of these suspects is sabotaging the factory.
Section 3. Iron deficiency versus chronic disease. Shortage or lockdown.
Okay, I absolutely love thinking about it this way. Imagine your body as a manufacturing plant. In true iron deficiency anemia, the factory shelves are just empty. You've either lost the iron through bleeding or you just aren't eating enough of it. Because the body is practically begging for iron, its total iron binding capacity, basically its eagerness to grab onto whatever iron it can find, is sky high. But its actual storage proteins, serum ferritin, is running on empty. It's extremely low. Now, compare that to the anemia of chronic disease. In ACD, the patient has some kind of underlying inflammatory issue, maybe an infection or even a malignancy. The body reacts to this threat by going into total lockdown. The iron is actually there, but the body locks it away inside a macrophage vault. It intentionally hides the iron so that potential pathogens can't feed off it. Because the iron is stuffed into that vault, the storage protein, the ferritin, is normal or sometimes even high. But the developing red blood cells, they still can't access it, so they end up small and pale anyway. It is this brilliant biological defense mechanism that just unfortunately causes anemia as collateral damage.
Section 4. Thalassemia and sideroblastic anemia. Flawed blueprints.
Let's look at thalassemia first. In this genetic disorder, the body's iron stores are totally fine. The actual problem is a failure to synthesize the alpha or beta globin chains. Those are the pieces that make up the hemoglobin molecule itself.
Because this vital protein isn't being built right, the resulting red blood cells are incredibly tiny. We're talking an MCV of 70 or even less. And that happens even if the actual anemia is mild. Actually, if a patient has the beta form of thalassemia trait, we can catch this specific suspect by running a hemoglobin electrophoresis. It'll show a uniquely raised level of a hemoglobin variant called HbA2.
Now, if you peek into the bone marrow, the visual evidence for sideroblastic anemia is just striking. Here, the defect is in the synthesis of heme itself. The cell pulls the iron in, but the assembly line is broken. It literally cannot incorporate the iron into the heme molecule. So what happens? The iron just piles up. It gets totally trapped in the mitochondria circling the nucleus of the red blood cell precursor, and it forms this beautiful but highly pathological blue halo. We call this a ring sideroblast. You do have to look directly at the bone marrow to see it, but man, it is a definitive piece of evidence.
Section 5. The diagnostic detective work. Solving the case.
All right, here is your diagnostic master key. Let's see how the lab values actually tell the story we just mapped out. Take serum iron, for instance. It's reduced in both iron deficiency and chronic disease. So, right off the bat, that alone doesn't solve our mystery. But then check serum ferritin, the storage protein. In iron deficiency, it's reduced. The shelves are bare. But in chronic disease, it's normal or raised. The vault is full. And what about thalassemia? Well, their serum iron and ferritin are totally normal because their issue is the genetic blueprint, not the iron supply. And finally, in sideroblastic anemia, the serum iron is actually raised. That's because the iron is just endlessly piling up around that nucleus, completely unable to be used. By cross-referencing just a few key metrics, serum iron, total iron binding capacity, and serum ferritin, our medical detective can accurately pinpoint exactly which mechanism is failing.
Section 6. Management and treatment plans. Fixing the factory.
At the end of the day, treatment is all about matching the solution to the specific crime. Step 1. If it's iron deficiency, the fix is pretty straightforward. We restock the shelves with oral or intravenous iron and, of course, figure out where the bleeding is coming from. Step 2. If it's the anemia of chronic disease, giving the patient iron will not work. Remember, their vault is already full. They just can't open it. You have to treat the underlying inflammatory or malignant condition to lift that biological lockdown. Step 3. For severe thalassemia, the factory can't be easily fixed, so we manage it with blood transfusions or folic acid support. Step 4. For sideroblastic anemia, the treatment really depends on the specific inherited or acquired defect that's causing the assembly line failure. This just perfectly illustrates why accurate differentiation is absolutely crucial. The wrong treatment doesn't just fail, it entirely misses the fundamental mechanism of the disease.
And that brings us to the end of our investigation. We've gone all the way from the macro scale of 500 million exhausted patients right down to the microscopic ring of iron trapped inside a single tiny cell. By understanding the body as a factory, by looking at the raw supplies, the storage vaults, and the blueprints, you can actually decode the invisible signals of disease. So I'll leave you with this thought. The next time you, or maybe someone you know, feels unusually and persistently fatigued, will you know what your red blood cells are trying to tell you? Thank you so much for joining me on this explainer, and keep learning.